Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to my AP Physics exam preparation video series. Over the next few weeks, I will be recording a sample video for each of the 4 AP Physics exams to show free response questions so that students can become familiar with what kinds of questions will be asked and how the AP Physics exam will be asking them to demonstrate their knowledge. As a tutor working with students all over the country, I know that not every student has the opportunity to work with released exam materials prior to exam day. Some instructors choose not to use the released materials, and others, especially some in independent and private schools, don't call their courses AP so that there's more flexibility in what can be taught, but those students will be taking the AP exam regardless. And this preparation series is really intended for students who don't have exposure to the released exam materials to help them prepare. The types of questions that AP Central lists for the AP Physics C Mechanics exam include one on experimental design or that has a lab-based component, and the questions altogether will assess all 7 of the science practices: visual representations, question and method, representing data and phenomena, data analysis, theoretical relationships, mathematical routines, and argumentation. Today we'll be taking a look at the C Mechanics exam from 2015, question number 2. We're looking at questions that span multiple topics, which are more common in the C exams than in the Physics 1 and 2 exams. And this question will look at projectile motion, conservation of energy and momentum, and simple harmonic motion. A small dart of mass 0.02 kilograms is launched at an angle of 30 degrees above the horizontal with an initial speed of 10 meters per second. At the moment it reaches the highest point in its path and is moving horizontally, it collides with and sticks to a wooden block of mass 0.10 kilograms that is suspended at the end of a massless string. The center of mass of the block is 1.2 meters below the pivot point of the string. The block and dart then swing up until the string makes an angle theta with the vertical. As shown above, air resistance is negligible. Part A, determine the speed of the dart just before it strikes the block. So at the top of its path, which is where it strikes the block, dart will be moving only horizontally. So we just need to find the horizontal component of its initial velocity, because that's the component that will not have changed. Remember that a projectile has constant velocity in the horizontal direction. So its velocity will again just be equal to that x component, which will be the initial velocity times the cosine of the angle. And when we substitute 10 meters per second and 30 degrees, we are going to get 8.66 meters per second. And as far as scoring, this one was simply +1 for a correct answer. And part B, calculate the horizontal distance d between the launching point of the dart and a point on the floor directly below the block. So that sounds an awful lot like, the horizontal distance traveled for this projectile. So to know how far it's going to go when we know the horizontal velocity, we're going to need the time in the air. So let me switch up my pen colors because that's kind of fun. Go. So we need to get time from the vertical information. We can look at how the vertical component of the velocity changes. Vy equals v naught y I should be more specific here, plus AY times T. Well, remember, our dart's moving only horizontally at the top, so Vy is 0, and it started off at 10 meters per second times the sine of 30 degrees for the y component, and then we'll have minus 9.8 times t, although you can use 10 for the AP exam. And when we solve this out, I'm not going to show you all the algebra, we're going to get 0.51 seconds. And now we can figure out that horizontal distance d by multiplying by the horizontal velocity times time. So we'll take our 8.66 meters per second that we just found in the previous part and multiply it by our 0.51 seconds here, and we're going to get 4.4 meters. And for scoring, we have +1 for a correct value for time. And then we have another point for substitution into an equation for horizontal motion. And that substitution is for a consistent speed. So we should say of a consistent speed from part A. So if you didn't have the correct answer in part A, but you used it correctly here, then you don't get dinged twice. And that is consistent across all of the AP exams, AP Physics exams. You can also earn this point for simply determining a correct answer. Part C, calculate the speed of the block just after the dart strikes. All right, so if you recall ballistic pendulum type problems, then you know that our next step is to deal with conservation of momentum for the dart striking the block. So we'll start off with an indication of our conservation of momentum. So initially we have just the dart moving, so we'll take its mass times the dart's initial velocity, which is the Vx that we found in part A. And then after the collision, we're going to have the mass of the dart plus the mass of the block times, I'm just simply going to call it V for after the collision. And so now we can substitute. We had 0.020 kilograms for the dart times the 8.66 meters per second from part A. And then we're going to add the two masses. And when we solve this, and again, I don't have all of the algebra shown for you today, but we will get 1.44 meters per second. And our scoring here, we've got +1 for a correct expression for momentum conservation. And I'm just going to abbreviate that MOM-CONS just to save time and space. Our next point will be that second line for a correct expression for a totally inelastic collision between the dart and block. And then our third point is going to be for an answer consistent with the speed from part A and for a correct mass substitution. So again, if you miss the speed in part A, but used your value correctly here, you only get docked once, but you do have to substitute the masses correctly. Part D, calculate the angle theta through which the dart and block on the string will rise before coming momentarily to rest. So if you recall ballistic pendulum problems, our dart's going to hit our block, and at that moment, we have all kinetic energy of the blocks because we're going to call the lowest point of the block dart combination where it can swing, we're going to call that height 0. So dart's going to hit the block, they're going to swing up and momentarily come to rest before swinging down. And so we want to figure out what is that height change between the lowest point of the swing and the height where the block comes to rest. So we have all kinetic energy at the bottom of the swing, and it becomes all gravitational potential energy. I'm going to call it position 2 at the top of the swing. So we are going to have 1/2 times the mass of the dart plus the mass of the block together times their velocity squared just after impact. We just found that velocity in the last part. And that's going to be equal to the potential energy, which will be, again, the sum of their masses times g times the height at position 2. So now on this diagram over here at the right, we are going to talk about how to find that h2. So I'm going to mark, first of all, the line. I'm just going to go at the top of the, where the block attached to the string, just for convenience. So that's going to be the height h2 through which the block rises. We're going to notice that over here, this dashed line is going to be the length of the string, and that is looking like a hypotenuse, and then this dashed line comes across, and we have a vertical piece that is like part of the string when it's vertical. I'm going to call that little piece lowercase l. And now we're starting to look like capital L and lowercase l, and this other little piece are forming a right triangle. And in here is going to be the angle theta to which the dart and the block on the string rise. So, a couple more things to note that are going to be very helpful for us are that this whole piece here, vertical piece, is also capital L, and then we have this little piece down here is h2, so we can say that h2 will be equal to the whole string length, capital L, minus this other little piece that I called lowercase l. We're going to be able to relate lowercase l to that angle using cosine. So the cosine of theta will be equal to the adjacent side, which is lowercase l, divided by the hypotenuse, which is capital L. So we can say that this lowercase l will be equal to capital L times cosine theta. So now we can come back down here to get our height, L, capital L, minus capital L cosine theta. And I'm going to take it one step further and factor out the capital L to make it capital L times the quantity 1 minus cosine theta. So now we have something we can go plug in for the height. And also notice here in this step that we've got mass equal size masses on both sides of the equation in both terms. So we can cancel that out, and we now have 1/2 v squared equals g times h2, which we just said is going to be L times the quantity 1 minus cosine theta. And I am going to go ahead and solve this out symbolically before I substitute. And I am going to get cosine theta equals 1 minus v squared over 2gl. So I would first of all isolate the term that has the 1 minus cosine by dividing by gl, and then I'm going to want to add the cosine term to both sides and then subtract the v squared over 2gl. Now I'm ready to substitute, and I'm going to get cosine theta equals 1 minus that 1.44 squared that we just saw in the previous part, times 2 times 9.8 times that 1.2 meter length of the string. And again, I'm not showing all of your algebraic steps here, but you will get an angle of 24 degrees. And let's talk about our scoring. So our first point is going to come for a correct expression of conservation of energy. It's also completely fine if you started off with kinetic plus potential at position 1 equals kinetic plus potential at position 2. I just left out the ones that we already knew were 0. Our next point is going to come from a correct expression for the height. I'm just going to abbreviate EXP for expression, for the height reached by the block. And my third time is going to be for substituting the speed from part C into a correct conservation of energy equation. I'm going to abbreviate that COE for conservation of energy. Part E, the block then continues to swing as a simple pendulum. Calculate the time between when the dart collides with the block and when the block first returns to its original position. So, if we're talking about time while a pendulum is swinging, well, that's period, right? So we can start with t equals 2 pi times the square root of L over G. And we can substitute our 1.2 meters, 9.8 for G, and we get a time of 2.2 seconds. But remember, if we're thinking about when the block starts from the bottom, although I guess I should draw that as, I guess it's a block, I should draw it as a block. So if we're thinking about, here is position 1 where we started, and then we're going to swing up to position 2. A complete swing would then take us all the way across to position 3 over here, same angle away, but on the other side. I don't have it drawn perfectly. And then we would still have to return back to position 1 to make a complete swing. So when we're talking about the time for the between when the dart collides with the block, that's position 1, and when the block first returns to its original position, that is only half of our, so we're going 1 to 2 back to 1, that is going to be half of a swing. So we need only half of the period. And so that will be 1.1 seconds. And our scoring here, we have 1 point for correct substitution of the correct length into a correct equation for period. And then our second point, oops, I didn't mean to write over top of that little scribble. Our second point will be for correctly dividing the period in half to solve for the time. Part F, in a second experiment, a dart with more mass is launched at the same speed and angle. The dart collides with and sticks to the same wooden block. Part 1, would the angle theta that the dart and block swing to increase, decrease, or stay the same? So here is my pro tip for questions like this. Justify your answer first, and then come up here and actually make your selection of increase, decrease, or stay the same second. Here's why. You can't correctly choose increase, decrease, or stay the same until you've already thought it through. And justify your answer is just writing out the thinking you have to do to make your correct selection. So, a more massive dart would cause the speed after the collision with the block to increase. A greater speed after the collision would cause the block to reach a greater height, and thus the angle theta increases. So our points here are 1 point for selecting increase, and then your next point will be for a correct justification of the larger angle for the dart block system. And in part 2, would the period of oscillation after the collision increase, decrease, or stay the same? Justify your answer. Same deal. Justify first. A more massive dart would not affect the period of the pendulum. You could even cite the equation t equals the square root, or t equals 2 pi times the square root of L over G. Only changing the length of the string would change the period. So we're going to select stay the same. And your points here, you get a point for, sorry, sometimes my cursor, I lose track of it visually. You get a point for selecting stay the same. It's really fun when I'm working on a computer that has, you know, an extra monitor or 2 attached. Can really lose track of my mouse then. And then you get 1 point for a correct justification. Boy, that got really messy. We're just going to fix that. All right, correct. Oh, for pity's sake. I swear I know how to write J's, like really, you know. There we go, justification. Oh, and I almost forgot. If the student correctly points out the changes to the simple pendulum could be outside the small angle approximation, then the student's entire answer will be considered. In other words, both the checkbox and the justification are consistent and physically correct. So I hope you found today's demonstration of this ballistic pendulum question that addresses projectile motion, conservation of momentum, conservation of energy, and simple harmonic motion all in one question. I hope you found it helpful. If you have a video solution request for me to put on YouTube, you can send it to physicsproblemrequests@gmail.com, although I won't actually be working on any of those until my AP series is over. If you need some email assistance, you can reach me at freephysicshelpline@gmail.com with a limit of 10 questions per academic year. If you'd like to learn more about my services, you can email me at brandyhevlinphysics@gmail.com. You can visit my website, virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. So just a few notes. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics C Mechanics exam, and those materials include the release free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different levels and quality of the responses that were prepared by students who took these released exams live, and to see what the scorers for that year were looking for and how they decided to award points. If you have any questions, you can reach me at brandyhevlinphysics@gmail.com. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.